Hi, guys. Can I get a shout out?
Yep, you're good.
Awesome. Thank you. Oh, stop. Stop that. Okay, guys, let's get started. Okay, so the first thing is um, we're kicking off with our first project. And again, until we figure out this cadence business, this is going to be a simulation project. So I've put this up, project definition up in Blackboard in the assignments section. And so I just wanted to go over it a little bit with you guys, given that it's sort of, I see this as kind of like our warm-up project. So I was trying not to make it too difficult, but also to start like sort of thinking through how we're going to do this. The first thing is that I would like the project report to be in the form of PowerPoint slides. I don't know if you guys do that a lot at Cal Poly, but you actually do a lot of PowerPoint presentations in industry or wherever you guys are going to go to work. Most of the stuff you do, I don't know, maybe it's half and half. So there's like, sort of Word documents that are written, but then if you're presenting results to management, again, it's like Power slides. So that's how I'd like you guys to do it. And I've got a very kind of specific thing that I'd like you guys to follow. It's what I do at work. And I'd like you guys to follow the same thing. So the first title, the first page is a title slide, and it just has the name of the project, like what you're doing. I always put in my name and contact information at work, in conferences, whatever, because that those slides take a life of their own. Somebody else might get the slides a few weeks and a few months, whatever, might have some questions. And if there's no, the presenter's name or the people who created the slides, their name and email addresses aren't there, they don't know who to contact. Okay, the second page, sorry about the typo there, is the intro. So usually in the intro, you're just sort of like just saying what's coming and the next, so what you're doing, why. People use bullets a lot. By the way, can you guys, has anybody not created slides in the class? So everybody's worked with slides. Okay, great. By the way, it doesn't have to be PowerPoint. It could be, I forgot what that Apple thing is called, whatever. It's just, pump it out as PDF, but it should be in the form of slides. Okay, so the third page is executive summary. Executive summaries are like extremely important once you get out of school, because most everybody has some form of attention deficit disorder, and the higher up in management you go, the worse it gets. So a lot of people are just only going to read that. So they're just not going to bother. If you have like a long list of slides, 15 slides, 10 slides, whatever, most of the people, especially the decision makers, aren't going to look at them. Some might. And if you don't include all those pages, you're going to get dinged, because if somebody's drilling down, they won't have the info. But most people are just going to want to see just short and sweet. What are your results? What's your opinion? What's the story? Okay, so last page is the conclusion, and then all the results are in the middle. Now, one thing to remember when you're making sort of slides for a presentation is that you always have a point of view. You are always telling a story in your presentation. It's never a neutral thing. It's never a graph of something, okay? If it's a graph of something, you have to specifically say that, what is the graph telling you? So you say, well, the theoretical and experimental graphs match, or the theoretical and experimental data or within the error margin, or the experimental data does not meet the theoretical data at all, and we recommend further study or something. There's always got to be, you always have a story that you're trying to convey. like that. And you make sure you do that in your slides. So that's one thing I'm going to be looking for, is that, you know, you have to, this number 5, you have to state like what's going on. You know, what is your point of view? If your results aren't what you expected, or they look funky, why, or what's your recommendation? Okay. And then finally, remember, this is like a pet peeve of mine. It's just non-scientific to not have axis titles, axis labels, and units for the axes. You see that all the time. Okay, you just see some graph, there's no units, there's no titles, it's just a horizontal axis, vertical axis, and some plot, and it's no good. Okay, so those are the ground rules. I'm gonna just grade the projects, like there's only like 4 grades possible. It's like 100%, 75%, 50%. Is that, no, wait a minute. 100%, maybe there's 5. 100%, 75%, 50%, 25%, and 0, right? So there's 5 things. So it's not going to be a bunch of nuanced grades. I'm going to be looking if how you guys did and whether you follow these rules. Okay, so here's the actual project, and it's going to be a simulation project. It's going to be a spice simulation, and you know, I'm going to put up a link to a presentation I put in YouTube on how to use LT Spice, which is what I have. It's a free spice platform. I think I talked about this last time. You can use that. You can use anything you like to do the simulations. But again, I can sort of help you guys debug if you're using LT Spice. So, but I'll leave it up to what you're doing. So this thing is like a warm-up project, and the idea is to look at a logic family that is not a CMOS logic family. It's a NMOS logic family, which was a precursor to the CMOS logic family. Now, why am I asking you guys to play with this old logic family? It's because, you know, a lot of the stuff we're looking at CMOS being a good logic family, you know, you're having different types of parameters, noise margins, delay, etc. That's good, is comparing it to something that's not good. And I think it's good to see something that's like this kind of not so great thing that we're comparing it to. Okay, and it's also sort of easier, at least in my mind, to understand an NMOS and inverter than it is a CMOS inverter. We're going to go towards analyzing a CMOS inverter very soon, but here's how an NMOS inverter works. This NMOS transistor on top here, you can think of the gate and the drain are hooked up together. Okay, so as long as this is a threshold voltage above the source, so the gate is at 1.8 volts in this case, which is the supply voltage. Okay, as long as this node is an NMOS threshold voltage below 1.8 volts, this guy's on and is sort of pulling this node up, and it's fighting with this guy. When this guy's on, okay, when this input voltage is high to this gate, the gate source voltage is large, and as this guy's on pretty hard, and it's pulling this output. It's on more than this, so its resistance is less than the resistance of this guy. Is going to pull this output node low. So the input is high, the output node is going to get pulled low, and when the input goes low, it turns off this transistor, and this guy will pull this output high until it itself turns off. Okay, so again, I think it's a fairly easy thing to understand. I think you've seen something like this in your previous classes, but maybe M2 would have been usually like a resistor. Okay, any questions about this? the circuit. You know, NMOS is pretty common. You guys can see the operation and different books on the web, etc. Okay, so a couple of hints here. It's that sort of referring to how, you know, our process technology lecture from the previous set of slides from the previous lecture. Remember that M1 and M2 are NMOS transistors. They're both sitting on the substrate. So both of their substrate contacts, that means the substrate, the body contact, whichever one you want to call, needs to be grounded. Okay, make sure you ground both of those. Okay, I'll show you what that means. And then the second thing is you can basically, the design sort of variable that you have when you're building your inverter is the relative width to length ratio of this M1 transistor and the width to length ratio of the M2 transistor. Okay, those are the two parameters you have to play with to get a transfer function or transient delay, etc. Okay, so there's 3 steps in this lab. The first one is you need to do a transfer function, a DC transfer function. And remember, this is in the horizontal axis, it's the input. In the vertical axis, it's the output. So it should look like, let me do this. Just give me 1 second, guys. Let me see if I can. Oh, can't share. Okay, never mind. So, okay, so basically you have to do a DC sweep on the input to look at the output. So let me show you guys what I mean. And I also shared this file on the, share. So I think it's this guy. Nope, of course I picked the wrong one. And not the right one there. Okay, there we go. Okay, so this is a LT Spice file that I put on Blackboard to help you guys to get a start. Notice both substrate contacts are grounded for both transistors. Okay, I have a voltage supply. For some reason, I call it VDD33. It's not, it's 1.8 volts. Okay, gate and drain on this transistors are connected. This is the input, this is the output. And then if you look here, this is just the way LT Splice works. There's a model for the transistors. So there's a model for the NMOS that goes from here to here. And there's a model for the PMOS that goes from here to here. So even if you're not going to use LT Spice, you may want to just cut and paste these models. You know, if you're going to use, I guess, PSpice or something like that, whatever you have access to, you'd want to use these. You have to put these models into your simulator. If you're going to use LT Spice, you can just use this file. Okay, so I'm doing a DC operating point analysis, and so this .dc is taking this VGSN, voltage source, VGSN, and it's sweeping it from 0 to 1.8 volts in 10 millivolt increments. Okay, so now it's not the nicest user interface in the world. So in fact, that was not helpful. So now I'm going to just plot the output. That plotted. And so you see now this is, I swept the horizontal axis. Can you guys see my cursor?
Yes, we can.
Okay, great. So the horizontal axis is the input being swept. and the vertical axis is the output. And you see it's a really crappy inverter, right? When the input is low, the output is high. When the input is high, the output is low. But it's got a bunch of problems. It's not going to the full supply voltage, either on the high or the low. It doesn't.
Excuse me.
Yeah.
We cannot see the graph.
I'm sorry?
We cannot see the graph.
Oh, you can't see the graph?
No.
Okay, let me see. Thanks. Let's see. Here we go. How about now?
Yes, yes.
Okay. So basically I'm plotting the output. So this is the horizontal axis is the input. Vertical axis is the output. And then again, this looks like an inverter only in the sense that the low input here gives you a high output. High input gives you a low output. But there's lots and lots of problems here. We described what makes a good inverter last time. This one is not particularly good. It doesn't go all the way up to the supply voltage. It doesn't go all the way to the ground. It doesn't have a prop transition. So I can now try to, let's see, go back to my, hopefully this is it. No, wait a minute. You guys see me changing a transistor size?
Yeah.
Yep.
So let's see. Okay, good. So sorry guys, I'm not quite sure what screen I'm sharing. So I'm going to make the length of this load large. So I'm going to make it 5 microns. So I'm going to basically make that load transistor be more resistive. Okay, and then I want to resimulate. Okay, and now I gotta share. Done. Okay, so now hopefully you see the graph again with the input versus the output, and you notice that I made at least I made the transition more abrupt. Okay, everybody see that? So
yeah,
basically that's what you're doing. Okay, so this is for part 1, and what you're doing is you are playing with those parameters, and there's all this stuff. Word. Okay, so now you should be back on the document for project 1. So you're doing this transient sweep. You're playing with the sizes, and you're getting them as good as you can. And what does good mean? In a DC sense, you're basically improving your noise margin low, noise margin high, and you want to see, the one you end up with designing, you want to say what is your noise margins and, how will it works. Okay, so that's part 1. Okay, part 2 is delay, basically seeing, we said this was how fast the circuit's running. So I have another file, which on Blackboard. Let's see, which one is it? Which is this guy, which is practically the same thing. All I did was I modified this guy to be the input to be a transient voltage source, and I just put some random, stuff on a pulse there, and then I changed the analysis type to transient. Okay, so now I'm going to simulate this. Okay, and we'll get the output. And then I'm going to put the input on there too. Nope, it's not what I selected. Sure. Okay, all right. So now you guys are seeing a graph with the horizontal axis being time. So do you guys see that?
Yeah.
And the vertical axis being voltage. Keep dropping my pen. So the blue waveform is the input. You know, it's going from 0 to 1.8 volts, staying high for a while, then it goes low. And this really crappy looking waveform that's green is the output. And you can see it's kind of like acting like a inverter. When the input's high, the output is low. When the input is low, the output is high. And so that's the setup you want for that particular simulation. And then from there, you got, so back to the document. And then the way you want to set up, which I did not, which is you want to have your inverter drive another 4 inverters like itself. This is called a fan out of 4 delay, or FFO4. We'll sort of see this over and over again. It's kind of a way of defining the performance of the logic gate. So make sure your inverter, whatever sizing it has, etc., is driving another 4 inverters like itself when you do that simulation. I didn't have a load, anything driving it. Okay. So, and also my recommendation is, so then you'll have an inverter and then another 4 of these guys sitting out here, and the output of this is driving all those inputs. As you'll see for problem 3, my suggestion is to keep the voltage source, the supply for this first inverter, a different supply voltage, not a different value, but actually a different voltage source than the other inverters, because you have to read something from there, but you don't have to do that. Okay, so for delay, so you have to do a transient sims, and then plot the waveforms, and then you want to actually read off the parameters for your delay, which is propagation delay rise, propagation delay fall, rise, and fall times. Okay, so I want to measure that in your graph, and you want to sort of state that. Okay, so that's delay. Lastly is power consumption. Okay, and basically what you do with power consumption is fairly easy if you're doing a transient simulation and you have your power supply separated. You basically just measure the current going through this supply of the first inverter, or you can just plot the transient current going through the drain of the inverter. If you've kept the supplies the same, you can do either one. Okay, so want to plot that. You want to plot it across for both a 0 and a 1 kind of output value, and also for the movements between them. So just go do 1 pulse low, 1 pulse high that are equal, equal in time. And that way you can also calculate the average power consumption, okay, by averaging the current across a low cycle and a high cycle and the transients. You can get the power consumption of your inverter, okay? So that's what you do. And then lastly, you want to see if this is the logic process you had, which is what people had before CMOS. How many could you put in a chip that was power limited? I mean, chips are power limited. So basically assume that 50% of these logic gates have a high, as you'll see, the current through this inverter is different whether the input is high or low. Okay, one has a lot of current, the other one doesn't. Okay, so just assume that 50% of them are 50% of them low. And then furthermore, you're gonna assume that the maximum power consumption you can live with on this chip is 40 watts, okay? Then working backwards, you wanna figure out, okay, I have 40 watts, I have a certain number of watts power consumption for the particular inverter. And then you just assume that all the gates are the same as an inverter. You want to see how many gates can you actually have in your chip with the gate that you design. Okay, any questions about this so far? I guess this is it. And again, I feel like hopefully it won't, you know, I kind of see this as a warm-up project to get you guys get going on simulations, but I think it'll give you an idea of these things like noise margins, transient, etc. And I've made this first one, try to make it fairly easy by having those 2 files up, so you don't have to sort of struggle with some of the stuff of getting your simulation stuff running, especially if you're using LT Spice. So, you know, so hopefully this is like a good first project for you. What else do I want to say about it? So I haven't thought of a good due date for this. I'm thinking maybe let's say probably like next Thursday. So I'll be like a week and a half. How do you guys feel about that? Anybody want to negotiate for any other amount of time? Going once, going twice? Okay, so next Thursday is the due date. Okay, I'll put that also on Blackboard. So anyway, all this stuff is on Blackboard. Okay, and so now we can jump into our lecture. Let's see. Just 1 second, guys. No. No. Yeah, I think so. Share device audio on. Okay. All right. So guys, this is where we left off, which was slide deck 3. Just what we went through was we saw how the CMOS process is kind of a step-by-step process where the manufacturing plant is sort of building up these various layers until you get your full, you know, the full process, which has, you know, transistors and the connections between those transistors. And then we saw how you have no control in the Z direction into the device. So like if by Z direction, I mean looking, you know, in the direction away from the, sorry guys, vertical to the surface of your chip. The only thing you can do is change the dimensions of the masks in the X and Y dimensions, which are parallel to the plane of your chip. So, and the way it's done is you basically look at each layer, you draw stuff on each layer. We went through how these things all kind of stack up against each other and make sort of the so-called layout of a device. So this is a layout of an NMOS transistor and a PMOS transistor that's made by a bunch of layers of different types stacked on top of each other. Okay, so that's what you have to work with to design a circuit. Okay. So, I want to say, okay. So now you can't just make these any size you want, okay? Because the foundries sort of created this process, like you can't make this too narrow, this gate. Otherwise they can't print it. Or, you can't put this piece of metal too close to another piece of metal. Otherwise they might get a short across it because they can only print things geometrically so well, okay, on the wafers. So this leads to something called design rules. Okay, so this is like usually like a document, and there's actually software tools that checks whether the layout you drew in software is also following these rules or not. And these are the guidelines given to you by the foundry about what they can make and what they cannot. Okay. And so they're always given for each layer, and there's like sort of like different types of design rules. Okay. So let me jump to first talk about what the different transistors look like, okay, before we talk about the design rules. Okay, so what does an NMOS look like? So NMOS, this is a NMOS cross section. This is the cross section over here. Okay, we have the drain, the source, substrate contact. Remember, this guy is P minus, sitting on a P minus substrate with all the other NMOS transistors, and this is the poly gate. Okay, so if you were going to look at this from the top down, this is what you would see. You would, or these are the different layers you would need to define this. First, you would need an active layer, so that would be sitting here. Okay, on top of that active layer, you would put the poly. Where there is no poly, so here and here, you would get the N plus source and drains, because then you draw sort of an N select layer on top. So N select tells the foundry that they're going to implant this area with N type material, right? It's going to be either phosphorus or arsenic, which is sort of typical N dopants. But the poly is acting as a mask, so you only get the N into the silicon in the source and drain. So that's how you end up with the source and this drain. Okay, so that in that point you have this, and then you put in the contacts. Okay, you need somehow to make a connection to the source and drain from metals that are sitting on top. So those are these drawings that tell the foundry to put holes there in the oxide. And then these guys are, it's hard to see it, but this dashed teal color thing is metal one. So they put metal one here. So it's connecting from metal one down to source and drain. So down to source and drain. Okay, it's a little hard to visualize. And then there's a couple of flavors on how to put the substrate contact, but the easiest one to understand is this. So remember we had the N select over active said put N implant here, but the poly basically masked off this area. So you only ended up with N plus here and here. So those are your source and drains, okay? Then you put an active here, and then you cover it with P select. So what's that telling the fab is they want to do a P implant over here. So you end up with a P plus there that acts as your substrate contact. And again, remember the substrate is P minus. Okay, you can kind of do it. This is a sort of a physically, you can get a smaller thing by butting up the P plus right next to the N plus, but you can't do that in every process. So it's kind of a, I don't know. And then sometimes you can have an N well, but I'm sorry, no, sorry. This is a PMOS layout. So I drifted off here thinking about P wells, but so this is a PMOS. So PMOS transistor, you basically have a similar kind of thing. You have an active drawing, you put a poly across it, and then you do a pre-select that tells it do a P implant everywhere. The poly protects the channel, and you just end up with P's on the sources and drains. But the PMOS is sitting in an N-well, and so you also have to draw an N-well layer here. Okay, so that's how you draw an N-type NMOS and a PMOS. Okay, and then similar idea with the substrate contact for the PMOS. Okay, and so those are the transistors. Then the transistors are planar in the sense that you can't stack up transistors. They're just either N's or P's or whatever. They're just the only way they can live is on the same plane. They just have to be next to each other. Now, interconnects or metal layers and vias, which are the connections between the metal layers, are in the third dimension, so you can stack them on top of each other. Okay, and they will not short to each other except where you have these via layers defined. Okay, so if you have this piece of this part of metal 1 is not shorted to metal 2, although they're drawn right on top of each other. I want to see if, let's see if there's a, so for example, here's an example. That's for the sake of this section, this is metal 1 and this is metal 2. If you draw it like this, those two will not short to each other because they are really on, we're looking at them from the top down. They're on different layers and there is no via drawing here that says connect those two together. Okay. So in this case, if this is metal 1, this is metal 2, these two would not short to each other. Okay. But if you draw two metal 2s, rectangles, they're on the same layer, so they will short. So this will look like, when the fab makes this will look like a cross laying on its side. Okay, and if you have, this is again an aerial view, so looking at top down, if you have two metal 1 rectangles sitting next to each other, they won't be connected. Or two metal 2s or two polys, they won't be connected, although they're in the same layer. Again, remember this, we're always looking at these layouts from the top down. Okay, what else do I want to say? Okay, so the connection, so the metal 1 is always the metal layer closer to the substrate, always. And metal last is always the last one. So I want to call this, let's call this metal last. I mean, it might be metal 3 or it might be metal 7, whatever it is. And then the numbering system goes from metal 1 to metal 2 up to whatever next to the metal last is, and then metal last. Okay. Most processes only have one poly, so you almost never see a poly 1 and poly 2 anymore, very rarely. So usually you only have one poly, and it's the poly for the gate. Okay, so this is kind of height. This is where the silicon surface is, and it's showing you that these layers are just on sort of further and further away from the silicon surface. Okay, so any questions so far about sort of this aerial view and So if you're drawing these masks in your computer-aided design tool, and the foundry takes those and makes the actual physical masks, and they use them in these different process steps to build up your transistors and your connections between the transistors. Okay, so those are a few things there. Sort of a contacts again, or anytime you have a metal one and either you want to get to a diffusion, whether it's N plus or P plus, either one would be called a contact, or if that metal one goes to a gate, that's called a contact. Okay, so those are the two things that this is a contact mask, contact layer. It's only from metal one to diffusion or gates. So one thing about contacts is contact resistance is relatively high. So, it might be several ohms to several tens of ohms, but that's pretty high actually, because I mean, if you think of about the resistance of a metal one line, that's like 1 micrometer wide, might be in the milliohms. Okay, 1 micron long, 1 micron wide. So if you have, something that's 2 to 20 ohms, which is a contact, that's a pretty high resistance. Okay. Another thing is, for whatever reason, contacts are prone to failing. I mean, the failure rate is very low. I don't know, might be, or the non-failure rate may be 99.9999, whatever, add the number of nines. But, it's something. And remember, all you have to do is to fail. You have a ton of them. And, if you got a 20 billion transistor chip, you might have, I don't know, no kidding, like 1 trillion contacts, who knows, maybe more, right? So, like, for none of them to, if any of them fail, if you use just one contact, like that gate or that transistor is knocked out, which means that gate doesn't work, which means your chip doesn't work, okay? So it's always a good idea, because of the relatively high resistance and the fact that, you might get a defective contact in all these contacts you're using, to use multiple contacts when all possible. This is like something you really want to do, which is use multiple contacts. You can make this N plus, for example, wider in your layout, and have sort of one contact, have two contacts sitting next to each other. If one of them fails, the other one works. And if they're both working, it's got, you've reduced the resistance. So always drop in multiple contacts if you can. Sometimes you're just remember, the chip area is the chip cost is a strong function of the chip area. So sometimes you're so pressed for making an area of your circuit or your chip small that you might go to one contact. But if you can, it's a really good idea to use multiple contacts in parallel. Okay. The same thing for via. So anytime you have any metal to any metal connection, you could think of it as a contact, but it's just called a via. Okay. And so you have via 1 that connects metal 1 and metal 2. You have via 2 that connects metal 2 to metal 3, and so on and so forth. So these are the contacts between the metals. So that's what you would draw to connect. So for example, again, if you have a metal 1 layer and a metal 2 layer without a via, they wouldn't be connected together because they're sitting on 2 separate layers. So you actually have to physically draw a via to short this metal 2 line to this metal 1 line. Okay. And again, the same thing we said for contacts goes for vias. they tend to have high resistance relatively, and they tend to sort of fail. Again, not very much, but your chip is full of vias. Okay. So overall, if you once you add all this, this is how you would lay out an inverter. This is an example. So here's a schematic symbol for an inverter. You know, we have we'll look at this in detail, the CMOS inverter. You have the NMOS pull down and the PMOS pull up. Remember the thing we're doing for the lab has an NMOS for the pull down and NMOS for the pull up. This is the so-called NMOS process. Okay, but the CMOS process, basically what it did was it replaced this with a PMOS transistor and connected to the gate of that PMOS as well. Okay, so here's the schematic symbol. This is what the layout looks like. Okay, so this is the layout of the transistors. Okay, so let's look through it a little bit. Okay, so this is the NMOS. This is the active layer. And this is the N select, which tells the factory to make that N plus. The polysilicon is protecting the channel. So you end up N plus here for the source and drain. And then you have active here and a P mask here. So you're telling the factory to put a P plus implant here. So it should be a substrate contact. So that's your body contact right there. And then you're doing something bold, which is using your poly for also to connect up. So you can think of this being this and this being this. So this is your input and this is your PMOS. And you got the active poly acting as a mask for the P plus. So you only get P plus here and here, and this is your substrate connection, and this is your N well. Okay, so this is your transistor. Now you want to actually connect this inverter to other gates, other inverters, etc. So you got to drop in your metals, your contacts, and your vias. Okay, so here's the input. Okay, you can think of this. This is metal 1. Okay, this is metal 1. This is a contact. So you put in 2 contacts to improve your yield and you reduce your resistance. So this is to your poly. Okay, so you've connected your metal 1 to your poly. Okay, here's your output here. Remember, the output is connecting to the drain of the PMOS and the drain of the NMOS. Okay, so you got a metal 1 and 2 contacts. Okay, so that's your output. And then you need to actually apply power supply and ground to this inverter. So you need to put contacts in for your source and your body here. And you've got a metal 1 overlapping it. And then you've got to hook it up to the power supply as well. So you put in contacts for that, a metal 1 for that as well. Okay, so sorry guys, just let me give me 1 second. I got a little bit of a noise issue. Let me go see if I can suppress the noise. Hold on a second. Sorry guys, there's like a dog party outside here in the living room. So All right. Hate to kill their fun, but we got business to take care of. Okay. So, any questions so far? And I know it's a little confusing without having the computer-aided design rules to play with, but you're basically overlapping these different rectangles or squares in different layers to build up your transistor definitions and connections between the transistors. Okay. Now, the design rules are telling you what, like if you can imagine if you're building these things, there's a couple of possibilities of failure. The first thing is you can make these rectangles too small. So again, looking at it from the top down, let's say you had your poly sitting on top of your active. Let's say this was n plus and n plus. Now, if you made this, I want to draw this poly in something looking slightly different color. If you make it really super narrow, they won't be able to print that in the fab in that particular process. Okay, so one thing they do is one rule they have is minimum sizing. So you'll see there's a set of design rules for the minimum size of like a poly layer. Okay, or the minimum size of in both directions. Okay, so that's one failure mechanism. Okay, the other one is minimum separation. So let's say you had two polylines that you did not want to connect. And for the sake of discussion, let's say you drew them too close to each other. And so the fab now basically can't quite print the separation, and this will turn into one hunk of poly instead of two. So they're also giving you a rule that says don't make these, and each one of these rules, by the way, is for each layer. You'll see a different number. Okay, but you'll see minimum size, you'll see minimum separation, and then some things like the gate over the active, or metal 1 over contact, or metal 2 over via and metal 1 over via. There's a minimum overlap. So this would be, for example, a metal overlapping a contact or a via. There's a minimum amount here because if I look at it from the cross section, if I had a piece of metal and I had a contact here that was going to contact to it, if I made that metal too small, I wouldn't be guaranteed a good connection to that contact. Okay, so these are the kind of rules you'll see. And I'm going to open up a design rule document. You guys can kind of see what I'm talking about here and all these things. Okay, so then lastly, this is just something for, really for universities. You never see this in the industry, but we have to cover it because like some of the rules you'll see in the book and the rule decks, or what you have access to are this kind of stuff, lambda-based design rules. What does this lambda-based design rules means? Okay, so this was an attempt by the sort of the university community to create like a universal set of design rules for a whole bunch of processes. Because universities, if you're doing research projects or university student projects, you kind of almost never know which fab you're going to go to. You might want to use different types of fabs. You might just have access to different fabs. So if you made everything in terms of this multiplying factor called lambda. So you can think of this as a multiplication factor. Then, and then you adjusted your design rules accordingly, you would be able to use this for different processes. So let's look at what this means, okay? Let's say you said, okay, my poly gate okay, so if this is, this green stuff is active, the red is poly, okay? So this is your poly, this is your gate length. Okay, so let's say we call this 2 lambda. Okay, so let's say in a 0.18 micron process, my lambda is 100 nanometers. I made lambda 100 nanometers. So when I give this drawn as 2 lambda, they're going to do 2 lambda. They're going to draw this as a 200 nanometer or 0.2 micron gate length. So that could work in a 0.18 micron process. Okay. Now let's say I was working with a 65 nanometer process and I made the lambda 40 nanometers. Okay, so 100 nanometers, 40 nanometers. So the same 2 lambda drawing would get made by the foundry as an 80 nanometer gate length. So it could be used in the same layout. All you have to tell the foundry, all you have to do is to give the foundry that, this other multiplication factor, and you can use it either in a 0.18 micron process or a 65 nanometer process. Okay. What do I think of this? Well, it served its purpose when the processes were older, for research and university stuff. Now, we have this in our class because we're a university, but you just do not see this in the industry. You're just giving away by making, just look at it here. To get a lambda-based design rules, I made lambda 100 nano here and 40 nanometer here. This means that although I have a 0.18 micron process, the smallest thing, the smallest length, transistor length that I could get is 0.2 microns. So I'm giving up sort of that performance. Instead of being able to draw 0.18 micron long transistors, I'm forced to draw 0.2 micron long transistors and have higher resistance, more area. It just adds up. It's just not as efficient. It's even worse here because although I have a 65 nanometer process, the shortest transistor length that I can draw is 80 nanometers. So again, I'm just, giving up a lot. This is sort of, I don't know, what 20% bigger than what I could make it, the minimum would be. So it's not very efficient, but this is kind of this is something people have done because, we're in university, etc. So it's sort of popular. So again, so every rule is defined in terms of these lambdas. So remember, we have minimum size, minimum separation. So this is like an example of a minimum size rule for polysilicon layer. The minimum size is defined as 2 lambda. Now, depending on which process you're in, whether 0.18 or 65 nanometer, the lambda means something different. Okay, and so this is like the metal widths. And then here the separations are also given in terms of lambda for each layer. And let's see what I want to say. These are overlap rules. Okay, so there's a minimum size of contact rule. So again, this is 2 lambda here. And then there's a minimum overlap. So the size of either the poly or the metal overlapping a contact, that's minimum size is 4 lambda that needs to get centered on the contact. Same with vias. So whether you have, in this case, metal 1, metal 2, and a via, the exact via size needs to be 2 lambda, and the overlap, meaning the size of the metal 1 or metal 2, it needs to be 4 lambda. And again, this lambda is 100 nanometers for a 0.18 micron process, or 40 nanometers for 65 nanometer process, or it could be different things for different processes. By the way, so you have, these are the rules you typically have. Okay, so you have the minimum size, minimum separation, minimum overlap. There's one exception, which is contacts and vias. And the exception is these have to be an exact size. Okay, so if a contact is 2 lambda, is the size of a contact, it means that it has to be 2 lambda by 2 lambda. You can't draw a 4 lambda by 4 lambda contact. It has to be the exact size. There's no minimum, there's no maximum, it's got to be exactly what they're telling you. So contacts and vias, or they're exact rules. Okay, so that's the definition. So it's just a bunch of different rules, blah, blah, blah. And this is an example of what you'll see in the document. Okay, so I'm not gonna, I put in this document on the Blackboard. So let me see if I can share it with you guys. Let's see. Where is it? Just 1 second, guys. And make sure I have it open. Doesn't look like I do. Okay. Okay, so you guys see something called CMOS restrictions?
Yeah.
So this is documents on the Blackboard, which is the set of design rules from the foundry. So just like, let's walk through them. There's some blah, blah discussions about how to read these rules. Let's scroll through these. So you can see, like, let's get something that's easy to absorb. So there's, like, again, these rules are very general. So there's a lot of stuff that is not necessarily going to apply to this 0.18 micron process we're going to be playing with. For example, there's no P base or whatever, this kind of stuff is not in this 0.18 micron process. So I'm trying to get us to, There we go. So here's a set of rules on polysilicon, an example. So here it's giving you, there's a bunch of different flavors of these lambda rules. I'll tell you which one we're gonna use in a problem or homework, etc. And then, so you'd have to use that particular column, either SCMOS, submicro, or deep. I think we're usually in the sub-M, but I'll let you know. So for each one of these, there is like a minimum width rule. So again, poly, so it's sort of defined. So this is 3.1, 3.1. This is minimum width of poly. It's 2 lambda. Okay. This is minimum separation rule, 3.2. Okay. There's different separations, whether you're on active. Actually, in this case, you see whether you're over active, meaning here, or over so-called field, which is any place other than active. You have, like here, you have whether you're on an active or not over an active, you have different rules for separation. And then you have this minimum extension of poly. Are you guys seeing my cursor?
Yeah.
Yeah.
I see it.
This is like a minimum extension of the poly over the active. Again, it's given in terms of lambda. So it sort of gives you an idea of the way the design rules are defined. So let's see another. So select tells you if you're N or P select. Poly 2 we don't have. So it just gives you guys an idea that this is the complexity of these rules. Okay, contact to poly, separations. And so you in effect, when you're doing the layout in industry or wherever, you have to use a combination of this document because you're drawing these things. But you will not ever be able to get it perfectly right. So they have these tools called, let me change the sharing here. So share screen. So you have this, oops, sorry guys, I'm having a hard time with the share. Okay. Okay, so you have a tool called DRC, which stands for Design Rule Check. Okay, using the software tool, basically all these rules are put into this thing, into this tool, that then checks them against the layout you've drawn, and it tells you if you've made any mistakes. Okay, so you really need that tool because the idea is you follow the rules, you draw something to the best you can, and then you run this DRC tool on your layout, and then that tells you where you've screwed up, and you start moving stuff around to fix these errors. You rerun the error checker. It says, okay, you fix these, but maybe you caused these other errors when you fix these, or you didn't fix these other ones. Then you sort of do that iterative process. You really need this design rule checker. If you did it just drawing and sending to the foundry, you're just guaranteed never to get the layouts right. But to create that starting drawing, you need to sort of follow the rules and see what they are to get the starting point. But then after that, you really rely on this tool. Okay, so the last thing I wanted to talk about is, I don't know if it makes sense to talk about this here. I think we should maybe talk about, let me leave this idea. This is like sort of optimization of your transistor layout to reduce your area in this case, or reduce your capacitance in this case. And this is this idea of you can actually overlap the layout of transistors because, for example, let's take this case. You have one transistor in A, one transistor in B. You don't need to contact so this point, this active, it's the drain of A and the source of B. So you can think of it as a drain of A and source of B is just one thing. You'll never need to electrically connect to this thing. There's no, as you'll see in the CMOS logic, is you won't be putting a contact here. This is like a AND function. If A and B are both on, you get this switch on. So it's kind of an AND function. We'll see that in the next in the next class. That's why I was thinking maybe better off waiting, but I can just sort of give you the gist of it. So because we don't need to drop an a contact here, okay, we can make this extra small. So you can kind of almost merge the drain of A with the source of B and get a smaller layout than if you fully drew an A with this and a fully drawn B with this source and drain, okay? So that's one technique that's very commonly used. The other technique that's used is to draw stuff, again, merged for type an OR kind of function. So notice that if this transistor is on, A is on, you'll get connections. Or if B is on, you'll get a connection. Or if they're both on, you'll also get a connection. So this is kind of an OR logic functionality, again, as we'll see in the next lecture. So here, notice that you can merge this guy, or you can merge this guy. So here's a merging of this stuff. So that's that merging. And here's a merging of this node. Okay. Now, and a MOS transistors are symmetric. So, you could think of this drain and source could be either one of these, right? This could be the drains of both transistors, or it could be the sources of both transistors, right? But this is, you can only have one be the joint drains and one be the joint sources. What one of them, it's more critical to have a low capacitance node. So for example, as we'll see, this node will be the output, which will be transitioning up and down. And so we want to make the capacitance of this node small, so we make that the merged node. Okay, we make that the merged node. And so it's lower capacitance in this node, and as you'll see, this will be grounded. So it doesn't matter what the capacitance is. Okay, let's see. This is another thing that's kind of will come up in SPICE simulations too, is because, like, let's say you want to have something twice as wide. So A goes to the gate that both the sources and drains are connected. So this is completely two parallel transistors. Same input, same drain, same source. And so you can basically use something called an M factor in SPICE and just say draw it once and put an M of 2, M of 3, as if there are 3 of them, 4, and so on. Okay. And then stick diagrams and stuff I'm really not going to go into. So let's stop here, guys. So this is kind of your design rule lecture. And unfortunately, again, we don't have, because of the being off campus, etc., we don't have access to this layout tool. So we're gonna have to kind of use our imagination a little bit about these layers and rules, etc., and just do what we can by hand, just enough to be able to understand how it's done. But we're not gonna get a lot of practice, unfortunately, doing these layouts. Okay, any questions, guys? Okay, if not, I'll let you guys go and see you on Thursday. Thanks.
All right.
Thank you. Bye.
Thank you.
Thank you, Professor. Have a good one.
Bye.